Hi all. In this video, we'll see about classification of the fluids based on the rheological properties. So normally, all fluids can be classified into two types based on the rheological properties, either as Newtonian fluids or non-Newtonian fluids. If there is a direct linear proportional relationship between the shear stress and shear strain or shear rate, then that fluid is termed to be as a Newtonian fluids. If there is no direct proportionality, then it's other way around, it's a non-Newtonian fluid. So that mathematical relationship, what I have described earlier, direct proportional relationship between the shear stress and shear rate is defined in equation 4.14. So here this is a shear stress, this is a shear rate, and there will be a proportionality between the shear stress and shear rate. And when the mu is a proportionality constant, when we put into that equation, then it becomes equality. Then that mu is termed to be as a proportionality constant, which relates a directly linear relationship between the shear stress and the shear rate. This is easily described in the graph figure 4.2. This is shear strain and shear stress, and when we draw proportionality between the shear stress and shear rate in the geometrical, it ends up in straight lines. The slope of the each and every straight lines will determine the viscosity. So if there is a high viscosity, there will be high slope. If there is a low viscosity, there will be a low slope of that particular straight line. But unfortunately, this relationship, that linear relationship between the shear stress and shear strain, won't be occurring for the most of the drilling muds that we are utilizing to maintain the proper hydrostatic pressures. So those drilling muds are termed to be as a non-Newtonian fluids. So non-Newtonian fluids again can be classified into different types based on their rheological properties, like Bingham plastic fluid model, power law fluid model, and time-dependent fluid model. So time-dependent fluid model in sense that there will be a change of viscosity as there will be a change of the shear during the time duration of that shear. So time independent doesn't happens with respect to the change of shear with respect to the time durations. So again, the time independent is Bingham plastic and power law fluid, and time dependent can be again classified as thixotropic fluid models or eupectic like Herschel-Berkeley model, which hasn't described in book, possibly will try to describe in later. So here the mostly the covered topic will be a time independent non-Newtonian fluids like Bingham plastic fluid model and power law fluid model. Like we described earlier, for Newtonian fluid model, there is a direct relationship. This is expressed in a mathematical relationship in 4.15 and 4.16. You see, if we are seeing in 4.14, there could be a proportionality constant, and it will be a direct relationship. But unlike there is a small variations with compared to the 4.14, it's an additional this term. What does this term says is, until certain shear rate, there won't be a fluid flow. So only beyond a certain limit, then the fluid flow occurs. So that threshold limit of the shear stress, which makes the fluid to fluid flow, is called as yield point, yield stress. Then after that, there will be a direct proportionality relations between the shear stress and shear rate. That proportionality constant will be called as a plastic viscosity. So this equations is geometrically described in this figure 4.3, and we know that until a certain shear stress occurs, there won't be a fluid flow, there won't be a shear rate, and once after that crosses a threshold limit or yield stress or yield point, then there will be a direct relationship, linear relationship between the shear stress and shear point. That proportionality, that slope of that particular straight line is known as a plastic viscosity. This is what it described here, and this is what described in this paragraph. So related to the power law model, this is what the equation 4.16, but it seems to be like kind of mathematically feels very difficult to digest. But when you're taking into a log scale, it appears to be like a Bingham plastics. Uh, the particular stress we needed to cross that limit, that intercept is related to the log k, and that n is related to the once after it crosses that yield point, then there will be a linear relationship between that stress in a log figure. Then that n is termed to be as a slope of that particular straight line. So this n is termed to be as flow behavior index, and log k is termed to be as a consistency index. This flow behavior index can take place a value between 0 to 1. 1 is termed to be as a Newtonian fluid, and between 0 to 1 is termed to be as a non-Newtonian fluid. This k indirectly in physics sense, it determines how thickness the fluid will be. The more the k, the more the thick, and the more it requires a large amount of initial shear stress for the fluid to flow. So how these rheological properties like viscosity are determined? So these are determined by using a special instrument called viscometer, and this is what a brief like overall diagram of that viscometer. It has like a rotational equipments and spring, and that spring how much it compress or decouplers can be related to this dial reading, and based on this dial reading and what rotations it rotates will determine the viscosity and the rheological other flow properties. For Newtonian fluid, for example, that it can for example any standard viscometer can have a 6 standard speeds, and those speeds can be varied, and those that based on the different speeds there will be a different dial rating for the particular fluid model. And once those readings are recorded, based on those recorded readings we can compute the viscosity free rheological properties. So but normally for a drilling mud, two standardized reading like 300 and 600 rpm would be sufficient enough to determine the required rheological properties. For Newtonian fluid, for example, when you are rotating at 300, and this would be termed to be as a viscosity, and this will be termed to be as a shear rate 4.17 and 4.18. For Bingham plastic viscosity for two readings like 300 to 600, and 2 can be 600 and 1 can be 300, and this is a dial reading, and that will determine the plastic viscosity and the yield stress. And related to the power law, we have two uh, two values or two variables, n and k, and n can be determined based on 4.23, which requires two readings like n1 and n2, 300 and 600 respectively, and these are dial readings. And once those the k also requires certain readings from measurement from the viscosity. Once that is k and k and determined, then that equations for the 4 point earlier what we have described as Bingham plastic fluid and power law model for determining the shear rate is close. So these two are the variables, and this can be determined from the viscometer, and this will determine the Bingham plastic fluid model and power law fluid model. Hopefully we'll in the next lecture we'll describe about what are the types of flow in pipes and annulus. Especially we'll describe about how the laminar flow occurs in pipes and annuli, what are the friction losses across the pipes and annuli are empirically computed, and we will discuss further about another additional properties of the laminar flow in pipes and annuli in the next video. Thank you.